What if the most complex part of training a language model to follow human preferences could be replaced by something as simple as logistic regression? That's essentially the provocative claim behind direct preference optimization, or DPO, a method that emerged from Stanford in 2023 and quickly became one of the most influential ideas in the alignment of large language models. The paper, authored by Raphael Rafaelov, Arkayit Sharma, Eric Mitchell, Stefano Ermon, Christopher Manning, and Chelsea Finn, tackles a problem that anyone working with large language models has encountered. These models learn from vast, messy internet data produced by people with wildly different skills, intentions, and levels of accuracy. You might want your AI assistant to know about common programming mistakes so it can fix them, but you certainly don't want it to reproduce those mistakes when writing code. The standard way to bridge this gap between what a model knows and what you want it to do is a process called reinforcement learning from human feedback, or RLHF. And RLHF works, but it is painful. To understand why DPO matters, you need to appreciate the machinery that RLHF requires. The standard pipeline has 3 stages. First, you do supervised fine-tuning, or SFT, where you train the pre-trained language model on high-quality demonstrations for your task, like well-written summaries or helpful dialogue responses. Second, you collect human preferences. You show annotators pairs of model responses to the same prompt and ask which one is better. You then train a separate neural network, the reward model, to predict these preferences. The most common framework for this is the Bradley-Terry model, which says the probability that one response is preferred over another is a sigmoid function of the difference in their reward scores. Third, and here's where things get hairy, you use reinforcement learning, typically proximal policy optimization or PPO, to fine-tune the language model to produce responses that score highly under the learned reward model, while staying close to the original model via a callback-Leibler divergence penalty. This KL constraint is essential because without it, the model will exploit quirks in the imperfect reward model and produce degenerate outputs. The whole process requires training multiple large models, sampling from the language model during the RL loop, carefully tuning hyperparameters for PPO, managing value function baselines, and generally juggling a lot of moving parts that can become unstable. DPO's core insight is elegant and, once you see it, almost obvious in retrospect. The authors start from the same KL-constrained reward maximization objective that RLHF uses. It's well known that this objective has a closed-form solution. The optimal policy is proportional to the reference policy multiplied by the exponentiated reward, divided by a normalizing constant called the partition function. This is nice in theory, but useless in practice because computing that partition function, which sums over all possible text sequences, is intractable. Here's the trick. Instead of going from reward to policy, they go from policy to reward. If you take that closed-form relationship and simply solve for the reward in terms of the policy, you get that the reward of any response equals beta times the log ratio of the optimal policy's probability to the reference policy's probability, plus a term that depends only on the prompt. And because the Bradley-Terry preference model only cares about the difference in rewards between 2 responses to the same prompt, that prompt-dependent term cancels out completely. Think of it like measuring the height difference between 2 buildings. You don't need to know the elevation of the ground they sit on, you just need the relative difference. The partition function is like that ground elevation. It vanishes when you take the difference. This cancellation is the key that unlocks everything. Once the partition function drops out, you can write the human preference probability entirely in terms of the policy you're training and the reference policy, with no reward model anywhere in sight. Specifically, the probability that response 1 is preferred over response 2 becomes a sigmoid applied to beta times, the difference in log probability ratios, the log of the policy's probability of response 1 over the reference's probability of response 1 minus the same ratio for response 2. This means you can directly maximize the likelihood of the observed preference data with respect to the policy parameters using a simple binary cross-entropy loss. No reward model to fit, no RL loop to run, no value function to estimate, no sampling from the model during training. You just need your preference dataset, your reference model, and gradient descent. The gradient of the DPO loss reveals something important about why this works and doesn't degenerate. When you take the derivative, you find that the update increases the log probability of the preferred response and decreases the log probability of the dispreferred response, which is intuitive enough. But critically, each example is weighted by how wrong the model currently is. The weight is the sigmoid of how much higher the implicit reward model rates the dispreferred response over the preferred one. When the model already correctly assigns higher implicit reward to the preferred response, the gradient contribution is small. When the model gets it wrong, the gradient is large. This dynamic weighting acts as an automatic curriculum and prevents the kind of degeneration the authors observe when you use a naive approach that simply maximizes the probability of preferred responses and minimizes that of dispreferred ones without any such weighting. It's like a teacher who spends more time on the problems a student keeps getting wrong rather than drilling the ones they've already mastered. The authors also provide a theoretical analysis showing that their reparameterization doesn't lose any expressiveness. They define an equivalence relation on reward functions. Two reward functions are equivalent if they differ only by a function of the prompt. Since such functions cancel in the Bradley-Terry model and also induce the same optimal policy, they then prove that for every equivalence class of reward functions, there exists a policy that represents it under the DPO parameterization. So you're not constraining the space of learnable rewards at all. The paper also offers an interesting diagnostic perspective on why PPO can be unstable. The normalization constant that DPO naturally handles corresponds to a soft value function of the reference policy, which in actor-critic methods needs to be estimated, often poorly, leading to high variance policy gradients. The experimental evaluation spans 3 tasks. In controlled sentiment generation, using GPT-2 large, the authors generate movie review completions and use a pre-trained sentiment classifier as the ground truth reward. Here they can directly measure the reward versus KL divergence frontier, and DPO dominates all other methods, including PPO with access to the ground truth reward. DPO achieves the highest reward at every level of KL divergence. For summarization using GPT-J on the Reddit TL DR dataset, DPO achieves about a 61% win rate against human-written reference summaries at greedy decoding, as evaluated by GPT-4, compared to 57% for PPO at its best temperature. DPO is also much more robust to sampling temperature. PPO's performance degrades sharply at higher temperatures, while DPO holds steady. In a head-to-head human evaluation, DPO summaries were preferred 58% of the time over PPO summaries. For single-turn dialogue on the Anthropic Helpful and Harmless dataset using Pythia 2.8b, DPO is the only computationally efficient method that improves over the preferred completions in the test set, and it matches or exceeds the performance of the best of 128 sampling baseline, which is extremely expensive at inference time. The authors also test generalization, taking the summarization models trained on Reddit and evaluating them on CNN or Daily Mail news articles. DPO achieves a 36% win rate against ground truth summaries at temperature 0, compared to 26% for PPO, suggesting comparable or better out-of-distribution generalization. The human study validating GPT-4 as an evaluator is a nice methodological contribution. The authors find that GPT-4's agreement with human judgments is comparable to inter-annotator agreement among humans themselves, lending credibility to the automated evaluation. They also note that the specific GPT-4 prompt matters. A prompt asking for conciseness produces judgments more aligned with human preferences than a simpler prompt, because GPT-4 otherwise tends to favor longer, more repetitive summaries. There are real limitations to acknowledge. The experiments use models up to 6 billion parameters, and while the method has since been widely adopted at larger scales by the community, the original paper doesn't demonstrate this. The question of reward over-optimization, where the model exploits the implicit reward signal in ways that hurt actual quality, is raised but not thoroughly investigated. The authors note a slight performance dip later in training for dialogue and wonder if this is an instance of over-optimization. There's also the question of how well DPO handles distribution shift. Since it trains on a fixed offline dataset of preferences, it can't explore new regions of output space the way an online RL method can. If the preference data doesn't cover the kinds of outputs the policy starts producing during training, the implicit reward signal may become unreliable. The authors partially address this by noting that you should initialize the reference model to match the model that generated the preference data, but this remains an open concern. And while the theoretical guarantees about expressiveness are clean, they rest on the Bradley-Terry model being a reasonable model of human preferences, which is an assumption, not a fact. Now let's walk through some questions you might have after hearing all of this. You might wonder why the partition function cancels so conveniently and whether that's a lucky coincidence. It's not luck at all, it's a structural property of the Bradley-Terry preference model. Because the Bradley-Terry model defines preference probabilities based on the difference in rewards between two responses to the same prompt. Any additive term that depends only on the prompt and the log partition function is exactly such a term, will appear in both rewards and cancel when you take the difference. This is the same reason you can add a constant to all entries in a softmax and get the same output distribution. Another natural question is what happens if you skip the importance weighting in the DPO gradient and just do naive likelihood maximization on preferred responses while minimizing likelihood on dispreferred ones. The authors actually test this, and the model degenerates. Without the weighting, the loss treats every example equally regardless of how well the model already handles it, which can push probabilities to extremes. The weighting ensures that examples where the model is already correct contribute little gradient, acting as a natural regularizer that prevents the optimization from overshooting. You might also ask whether DPO is truly equivalent to RLHF or just an approximation. It is mathematically equivalent under the Bradley-Terry preference model. The authors prove that the reparameterization from reward to policy covers all equivalence classes of reward functions, so no expressive power is lost. The difference is purely computational. DPO solves the same optimization problem but arrives at the solution through a direct classification loss rather than through the RL detour. The only practical gap is that DPO works with a fixed offline dataset, while PPO-based RLHF can sample new responses during training, which could matter if the preference data doesn't adequately cover the policy's output distribution. For anyone building large-scale recommendation systems, the core idea in DPO, bypassing explicit reward modeling and RL by reparameterizing the reward in terms of the policy itself, maps directly onto several practical challenges. In recommendation, you often have pairwise preference signals. A user clicked item A over item B, or spent more time on one piece of content versus another. The standard approach is to train a pointwise reward or relevance model and then optimize a ranking policy against it, sometimes with bandit or RL methods that are similarly finicky to tune. DPO suggests you could instead train your ranking policy directly on pairwise preference data using a simple classification loss, where the policy's own log probabilities serve as the implicit reward. This could dramatically simplify the training pipeline for user-facing ranking models, eliminating the need for a separate reward model and the instabilities of online policy optimization. The dynamic importance weighting in DPO's gradient is also relevant. It would naturally focus training on the hardest pairs, the items the ranker currently gets wrong, which is a form of hard negative mining that emerges for free from the math. For systems serving billions of users, where you need to retrain or fine-tune ranking models frequently, the computational savings from dropping the RL loop and the reward model could be substantial. And the stability improvements could mean fewer failed training runs and more predictable model updates.